The next thing we're going to work on is predicate calculus. So we got to take a little break from logic by doing logic circuits. So we got to take a break from the proofs just for a few minutes. But now we're going to go back to some logic again. So remember that when we first started logic, we had some statements that weren't propositions. They were things that we couldn't tell whether they were true or false, so we couldn't use them in logic. So statements like that were things like x equals 5. And so that's not a proposition because we can't tell whether it's true or false just by looking at it. But if I knew a value for x, then that would be a proposition. So 1 equals 5 is a proposition. It's a false one, but it is a proposition. There's another way we can talk about propositions, make x equals 5 into a proposition, and that is to say, we might say something like, for all x, x equals 5. So this is a proposition, and what's its truth value? Is that a true statement or a false statement?
You don't know.
No matter what x value I plug in, do I get x equals 5? So if I set x equal to 1, I get 1 equals 5. Is that true?
No.
It's false, right? 1's not equal to 5. So this statement is a false statement. But it's a proposition, so we've actually converted it into something that we can do logic with. Because we couldn't do any logic with x equals 5. Now we can actually do some reasoning about things because we know that this statement is false. It's not true that every x, no matter what I plug in, x equals 5. Now, how do you know what kinds of x's to plug in? Does anybody know? I could plug in dogs, right? Because I didn't say. No one told you what you could plug in, right? So when you see something like for all, you need to ask, well, from what set? Okay? So we're going to have a universe. It's called, this is the math term for it, the universe of discourse. And so in this case, I would want to say, perhaps I might say that x is the integers. So I'd really write, if someone were, a mathematician, I would say for all x, and this symbol means is a member of, or simply in, z, and z represents integers. For all x in z, x equals 5. That's my predicate, and it is false. So a predicate is a statement that would be a proposition if you could plug in a value. So it's basically a function. It's a logic function. It has inputs and it has logical outputs of either true or false. So let me write that down, that a predicate is a function. And we always have to have a domain or a universe of discourse for my variables. So we found two ways so far to make statements into propositions. So we could plug in values. If we have a statement that has variables, we can either plug in values for the variables, or we can say the statement is true for all values of the variables. And does anybody have any other ideas of how we might make a statement with variables in it, how we would make it into a statement that's either true or false.
It's true for some.
That's right. We could say that the statement
Or at least one.
is true. That's right. For some, or at least one value. So in logic, we're going to consider some and at least one, we're going to consider those as the same. Because some, in English, a lot of times we're going to think it's like more than one, that it has to be at least two. And some people might even argue with you that it needs to be at least three if you're going to say some. But in this class, some means at least one.
At
Okay.
least including one?
Yes, at least greater than or equal to one. At least one means one or more. Okay, so we have, as you may have guessed, we have funny ways of writing for all and at least one, because it wouldn't be torturous without them. So for all, we would rewrite for all x equals 5. First of all, we would define a predicate. We would say P of x is that x equals 5. That's my predicate, P of x. Then my predicate statement would be for all x, P of x. So this statement, this upside down A means for all. And someone invented that a long time ago, and we're going to have to use it. So we also have a way to write there exists. And that is a backwards capital E. And so the way I remember these is all has an upside down A and exists has a backwards E. And maybe they would have made the E upside down, except it looks the same upside down. So they had to make it backwards. Okay, so these are how we write predicates. And now these are propositions. This is a proposition because it's either true or false. Either it's true that for all x, P of x is true, or it's false. And there exists x, P of x is either true or false. There's either one or there isn't. And I should be able to check. So in this case, when P of x is that x equals 5, for all x, P of x, we already said was false. What about there exists x? That's true, assuming our universe of discourse is still the integers. X equals 5 is our example that makes that true. So in this case, if this is true, I should be able to write down the value that makes it true, right? So that's a good habit to get into. If you have a there exists that's true, it's a good habit to just write down the value that makes it true so that when you look at it again, you can assure yourself that it really is true. If you can do it. Sometimes you can't. Okay, and so since these are propositions, they work just like other propositions. So once I've made a predicate into a proposition, I can use it just like I use regular propositions. So if for example, I could use De Morgan's with these. Okay? So if I had for all x, P of x, and there exists x, Q of x, each of these values is propositions. So I could apply rules to it. So if I put a not on that and I want to use De Morgan's, I can do it. Because each one of these is a proposition. It's just a variable. So De Morgan's on this would be not the quantity for all x, P of x. Change the and into an or, and not the quantity there exists x, Q of x. So that's using De Morgan's rule, and most all of our rules can be used that way. Let me just tell you one convention so you don't ask me later. Where do you think the for all x in that statement applies?
Left to right.
It applies to every single x that comes after it. So I don't need to write parentheses, although some of you may feel better if you write parentheses. I don't need to write parentheses because the x applies until I redefine it. If I redefine it, as in this statement up here, this x is a different x than that one. Okay, so this is going to work just like variable scoping in your programming. So this is the definition until I redefine this variable. So I don't need parentheses for that.